In the last two videos, we took a look at a box that was filled with water, or a rectangular solid, and then we took a look at a cylinder that was filled with water, and we tried to figure out the work that was necessary to pump all the water out of those tanks. So now we're going to take a look at an inverted cone. All right, so a final shape that we have. And this time the height is going to be 8 meters, the radius is going to be 2 meters. And so we know a cone looks something like this, all right, but it's going to be inverted. Okay, so in other words, we're just going to flip that over. And so what it looks like for an inverted cone is it's going to look something like this. All right, we know that the radius, r, is going to be 2, and we know that the height, h, is going to be equal to 8 in meters. All right, we're going to use our work formula, the same one that we've used to pump all of the water out, 0 to h. We have our area for our cross sections, a of y. And then we have our density, we have our gravitational constant, and then we have our height minus some value y, a variable dy. Right. Now, if we know that we have 1,000 kilograms per meter, and we know that the density of water is 9.8. So right away, we know those two animals. That's pretty easy. All right, those are given. We know that the height is 8 meters. All right, so h is going to be 8, and then this is going to be 8. All right, but these are always the tricky things to get the cross sections, and cross sections the area. So if I draw the cross sections, all right, this is what I'm getting. Okay, so what it looks like is that I'm getting circles of varying radii, and so we have to find a relationship of the radii to this cone. All right, and one thing that we can do is we can construct these sorts of triangles. Okay, because if I draw a vertical, notice that we get a triangular shape. All right, and just imagine that that does go down the length of the cone. And so notice that the radii are just going to be the distance from some point inside, and there's going to be a relationship. Okay, so this is like our x and our y. Okay, and this is our x and our y. Okay, so notice that there's a bunch of triangles that are inside of this sort of cone. All right, and that's what we're going to do is we're going to find a relationship of these triangles to be able to figure out what's going to be the area of, or actually what's going to be the radii of each of these different circles. All right, so what we can do is we can say that, let me get rid of all this stuff right here. All right, just so that way we can kind of work with this, okay, and I'll draw a couple circles back in there, okay? So what we can do is we can try to get some sort of relationship here, all right? So here's a circle and here's a circle. And one thing that we know is that this, if we treat this like an origin, like 0, 0, the top point right here, and I'm going to exaggerate it just because of the screen, we know that the distance from the origin would be 2 to the right and 8 units up. And so what that means is we can kind of get an equation of this line. So we can get y equals something. And so we need the slope. Okay, so that's going to be y1 minus y2, all right, or y2 minus y1, and then x2 minus x1. And that's going to be 4, right? And then consequently, we can say y minus y1 is mx minus x1. Let's just use the origin for y1 and x1. So y minus 0 equals 4x minus 0, which implies that we get y equals 4x. All right, so this line right here is y equals 4x. All right, but because we're trying to pull all of the water out vertically, it may be better for us to get a function of y. And so y over 4 is going to be equal to x. And remember, x is going to be the radii. Okay, so remember we had like x, and we had an x, and we had an x, and we have an x value. Okay, now we know that the top radius is 2, but what are these varying radii? And the varying radii, x, are going to be our radii for this. Now we know that the area of a circle is going to be pi r square, all right? But we know that x is the radius, but also y over 4 is the radius. So this would be pi times y over 4 square, or y squared pi over 16. And so this is going to be our a of y function. And we're just going to substitute it right back into the work formula. Okay, so let's do that and then compute. So this is going to tell us that our work is going to be equal to the integral from 0 to 8. Okay, so remember we said the height was 8. We're going to use our newly found y squared over 16. We know that the density is 1,000. We know that the gravitational pull is going to be 89.8 meters per second square. And then we know that the height is 8, y is variable, dy. All right. Now, we're going to get all of this outside as a coefficient, and then we're also going to distribute the y square to be able to integrate this. Okay, so if we do so, and I'll use my fancy calculator, all right, this is going to be 1,000 times 9.8. And then we also have our 16 that we have to divide by. All right, so I get 612.5. All right, and I'm just going to pull that out. So our work is going to be 612.5 pi, integral from 0 to 8. And then we also distribute the y squared. So that's going to be 8y squared minus y cubed dy. All right, and now we just integrate. All right, so we have our 612.5 pi. We're going to have our 8/3 y cubed minus 1/4 y to the 4th from 0 to 8. Fortunately, 0 doesn't contribute anything to the sum. All right, so that's just going to be a 0. So it's going to be 612.5 pi, 8 times 8 cubed over 3 minus 8 to the 4th over 4 minus 0. Now, this could clearly be written right here as 8 to the 4th. Since we have 3/8 and 1/8, that's going to be 8 to the 4th. So I'm just going to write that as 8 to the 4th. All right. And I'm just going to throw this into Wolfram Alpha just to make it easier for us. All right. So if we throw it into Wolfram Alpha, all right, it gives us 627,200 over 3. All right. Or if you want to make it easier or harder on yourself, I'm not sure why it has that, but rational approximation. So good for them. So it's going to be 627,200 pi divided by 3. All right, so that's the exact value. And the unit will be in joules. Notice that everything is in meters, okay, and also kilograms, cubic meters, meters per second square. So we have all the SI units. All right, so it's going to stay in that SI unit. All right, so now the second part of the problem says, is it true that it takes half the amount of work to pump all the water out of the tank when filled to half depth as opposed to when it's full? All right, and we're going to explain why. So let's just change the height to 4. All right, so now what we're going to do is we're going to say, all right, well, I'm going to change this animal right here to height. I'm going to call it h sub 2 is equal to 4. All right. And we remember from the previous problem that certainly it's not going to be true because of the distance. Okay, so remember, the further we are from the top, the more work it's going to take. All right, the closer we are to the top, even though it might be a little bit bigger, all right, it's going to be still easier to pump out. All right, so we're going to do the exact same integral, and I'm just going to pick it up from right here, except I'm going to change the bounds to 0 to 4. Okay, so our work is going to be equal to 612.5 pi, integral from 0 to 4. All right, this is part B. 8y squared minus y cubed dy. All right. In fact, we could probably just pick it up from right here if we elected to, since we already have the integration. But since it's Calc 2, it couldn't hurt to integrate a little bit more. So 612.5 pi, 8y to the 3rd over 3 minus 1/4 y to the 4th from 0 to 4. And then this just becomes our 612.5 pi, 8 times 4 to the 3rd over 3 minus 1/4 4 to the 4th minus 0. All right, Now, this is actually pretty cool because we have a 4 to the 4th over 4, so we could actually cancel one of these out and actually make it into 4 to the 3rd. All right, just to simplify it. So this would be minus 4 to the 3rd, all right, or 3 4 to the 3rds, all right, if we got a common denominator, but we could just stick this into Wolfram alpha. All right, so really quickly, I'm going to do that. All right, so we had 612.5, and then we had a quantity of 8 times 4 to the 3rd divided by 3 minus 4 to the 3rd. All right, and that should do it. Get rid of this extra parenthesis. All right, and so what we end up is 19600 over 3. Okay, so that's going to be, go back. This is going to be equal to 196,000 pi over 3. Okay, and that's going to be in joules. All right, and let me just make sure I didn't copy that down incorrectly. 196,000. Now, this should be, if we're going to test to determine, this should be half. Okay, so what I'm going to do is I'm just going to multiply this by 2. Okay, so this is from depth of 0 to 4. Okay, and so if we double it, and that's what the question's asking, is if we double it, should it be the same? So I'm just going to take 196,000 pi over 3, and I'm going to double it. So I'll just take that 196,000, multiply it by 2. All right, and that gives us 392,000. So this would be 392,000 pi divided by 3. All right, that's in joules. All right. And clearly, that's not the same as what we got for our first answer, right? So remember, our first answer was like 200,000 something. Okay, so if we go right here, or actually 600,000 or 627,200 over 3. All right, and that's clearly not the same. All right, so that's not equal to our 627,200 divided by 3 joules. All right, so clearly it's not the same. All right, so hopefully that's helpful for everybody to understand how to go through and determine the work necessary to pump the fluid from all of these. All right, and just a recap of all of the different types of problems that we looked at for work. Okay, so we looked at mass in the first video, and then we took a look at being able to do the work problems, and the different work problems were just like a basic work problem where we had a variable force over a distance. All right, we had the spring problems. All right, and then also we certainly had the fluid flow problems, which we just finished. And then the last one we had was the vertical distance, or the lifting problems. All right, so make sure that you have all 5 of these types, the mass and then the 4 types of work problems. Make sure you have those down for the examination. All right, because generally on an examination, I'll probably ask you like maybe 1 or 2 of those different types in addition to all the other types of problems that we have. All right, so that's going to be it for this section. And actually for all of our applications of our integration. So in the next section, we're going to start deviating from this and take a look at a new topic.